In this example, we are looking at the set of all rational numbers of the form n divided by 2. Notice they are listed in this set. The n that's in the numerator is an integer. It could be 0, 1, 2, 3, or -1, -2, -3, anything in the negative direction or anything bigger in the positive direction, as long as we're dividing by 2. And notice that 0 is in this set, because you could also do 0 divided by 2. That equals 0. So we've just simply put 0 in the set. So is S closed under addition? If you try 1 over 2 plus 2 over 2, you get 3 over 2. If you try 2 over 2 plus 3 over 2, you get 5 over 2. You're adding halves together. If you have a certain number of halves and you add another certain number of halves, you get a total amount of halves. So this seems like it should be a closed set. Let's see if we can prove that it's closed. So I'll dig my hand in the set. I'll pull out an a divided by 2 and a b divided by 2. This represents anything in my set S, and I'll try to add these numbers together. A over 2 plus b over 2. So when we add a over 2 and b over 2, that's the same as a plus b over 2. The a plus b represents an integer, because a and b themselves are this numerator that was an integer to begin with. So the result of a plus b divided by 2 is indeed in our set S. Is it closed under subtraction? This is a very similar story. A divided by 2 subtract b divided by 2 is a minus b divided by 2. A minus b is also an integer, so in the numerator I do have an integer, and I can say that I have an integer divided by 2. The numerator could be negative, it could be positive, but negative halves are still in our set. So this is perfectly fine to always end up in our set S. What about multiplication? So if I multiply a over 2 by b over 2, what happens? We could write a b over 4. So we might get a quarter out of this. This doesn't seem like it should be closed. Let's try a counterexample. I don't want to report my answer like this. It looks like I'm trying to prove that it's always within the set, but I seem to have discovered that I could make a quarter. So following a similar example to how we did for addition and subtraction doesn't seem to me like it would work out. I could maybe do something like 1/2 multiplied by 1/2. That gives me 1/4. 1/4 is not in the set. 1/4 is bigger than 0, but smaller than 1/2, so it's certainly not in my set S. So it's not closed under multiplication, while it is closed under addition and subtraction. Let's try division. So we could do something really similar here to what we did for multiplication. We can probably try to dream up a way that you could get something other than 1/2. So how about we try to produce 1/4 like we did above? So 1/2 is in our set. How would we divide 1/2 by something to get 1/4, which would not be in our set? And we could finish off the problem by saying no, if we could do this conclusion. So what could we write here to show that we can divide 1/2 by something to get a quarter. If we could write 2 right there, 1/2 divided into 2 is indeed 1/4. So that would work. That would show that no, I am not closed under division because 1/4 is not in the set. But is 2 in our set originally? Remember, you have to only take halves. So think about this for a moment. Is 2 in our set that only contained halves? Now, if we think carefully, 2 is indeed in our set because 2 is the same as 4 halves. So this is perfectly fine to write 2 in our expression because it is one of the numbers within our set. 4 divided by 2 is equal to 2.